Hello everyone. So in this lecture, I'm going to start to drive the energy equation in fluids, and then we will use this energy equation to drive the Bernoulli again, but now with respect a more general form of Bernoulli that also accounts for frictional forces. So the one that we previously derived, if you remember, was only for inviscid flows, but here in the new derivation, we also account for the friction losses. And so this will be a more general way of derivation of Bernoulli, which comes from energy equation, unlike the previous one, which we derived it from the momentum equation along a streamline. Okay, so let's get started. So for the energy equation, the first law of thermodynamics states that the time rate of increase of the total stored energy of the system equals to net time rate of energy addition by heat transfer into the system plus net time rate of energy addition by work into the system. Okay, so the total time rate of energy stored into the system equals to the heat transfer plus the work that is been done on the system. Okay, and now this is let's write this in terms of mathematical operations. So we have the time rate of change of the total energy stored in the system. So what is the time rate? We show it with derivative d over dt of the integral over the whole system of internal energy of the system, which I call and show it with E, the internal energy per mass times for all components rho dV, integral of that, right? So E is the energy component of just one small component of the system, say like this dm. So E is the energy of that, and then you want to integrate, E is the energy per mass of that, and so you want to integrate that along your whole system. So you just get the sum of the whole energy of the system. Okay, And instead of dm, I just wrote as rho dv. Okay. So this is how it's shown here, and this equals to the first term, which shows the net heat transfer into the system, which I show it as sigma q dot in minus sigma q dot out of the system plus the work done into the system, which I show it as W. So this is going to give me the Q dot net in, the total, the time rate, the net time rate of energy addition by heat transfer. I show it with Q dot net in, okay, plus the total work done in the system. So the internal work, I show it with W dot in minus the sum of the W dot out to the system. And this is going to give me W dot net in. Okay. Which I can write this. Let's now see what are these. Okay, so we have the heat transfer, which is we show with Q dot, and then the net of the work done on the system. So this is how the energy in the system varies with time, and this is the first law of thermodynamics. Okay, so let's see what is the internal energy. So E is internal energy per mass which I show it as, so this E is has these components. So it has internal energy per mass, which is U. I show it with U. It's the total energy of the system, right? So it's internal energy plus kinetic energy. So kinetic energy per mass, which I show that as V square over 2. And then plus potential energy, again per mass, where for potential energy I show that with GZ. Okay, and so the total energy of the system equals to the sum of the internal energy plus kinetic energy, V squared over 2, plus potential energy, GZ. Okay. Now let's look at W dot. So that for W dot, I can decompose the total work by the work done by the pressure and work done by tangential stresses. Okay, so I can say this work is composed of delta W dot of tangential stress, like frictional forces, plus work done by the pressure. So I show it work by pressure, and for work by pressure I show this by minus the integral over the control surface of rho V dot N dA. Okay. Let's see if we have everything here. Yes, okay. So let's now use Reynolds transport theorem. So use Reynolds transport theorem for this term, theorem for E rho, right? And what was the Reynolds transport theorem? So if you remember, we had dB system was equal to, over dt equal to the integral of rho b dv plus the integral over the surface in control surface of e rho b v dot n, right? So now instead of b, we just set e and write this down. So we have d over dt of the integral over the system of e rho dv equals to partial t integral over control volume of e rho dv plus the integral over the control surface of e rho v dot n dA. Okay. So I can write this as, instead of E, here, instead of E, I just write down the definition that we had, okay? And also, what I'm gonna do is, I forgot to add something here. Let me make sure I have it. This is gonna be, yeah, I think I wrote it wrong. Yes, so let me first write it down and then I will correct it. So I have the integral over the control surface of E rho over the control volume. Let me write it down. So it equals to partial over partial t of integral over control volume of E rho dV plus the integral over the control surface of, instead of now E, what I want to write is this definition, the expression here. So I write it as U plus V squared over 2 plus GZ times rho V dot N dA equals to Q dot net in, which is the right hand side, right? Right hand side of this. I want to write this down. Q dot net in plus, for this one, I can write this delta W dot tangential stress. I can just write it plus W dot of shaft in and then the work done by the pressure is going to be minus integral over the control surface of, this was P. I think I wrote it incorrectly. This is going to be the work by the pressure. So let me fix this. This is P. So it's going to be minus PV dot NDA right? And again, this is going to show me the work done by the pressure. So this is the decomposition of the W dot net, right? That I had. And so now that I have this, I can rearrange the terms to get a simpler form. Okay, so let's do that. So this is gonna give me partial over partial t. Let me just let me see if I can copy it. Okay, that would be easier. So equals to this. Now here, instead of this, what I'm gonna do is I'm gonna take this term to the left hand side because they are similar to each other. So I have this plus P over rho times rho V dot N dA equals to Q dot net in plus W dot the work done by this or the system by shaft. Let's say if you have any pump or any shaft. So this is a very important formula, as you see, and we are going to further simplify it. Okay, so let's see what is this term, the integral or the control surface of U, the internal energy, plus P over rho plus V square over 2 plus GZ rho V dot N dA equals to. So the integral over the control surface, as you remember, we can say for the flow out, this V dot N is going to be positive number, right? For outflow. And for inflow, if you have something like that, so if for outflow, it's going to be positive, and for inflow, it's going to be negative, right? So this is what we had from the momentum equation previously. So I can write this as follows. So I can write, or for all the flow out, this is going to be U plus P over rho. This term you know, right? It's going to P over rho plus V square over 2 plus GZ. And then instead of volume flow rate, I can write it as mass m dot. So that was another way of writing the momentum equation, if you remember. Okay. And then minus all the flow in is going to be has a negative sign. So it's minus this quantity calculated over the inflow region for with m dot, right? So this is m dot out, this is m dot in. Okay. But these two have to be equal, right? Whatever comes in from mass should go out from the continuity. So I just assume they are the same. And so in one dimension, I can write this as, for example, if you have a pipe flow, or in one dimension, I can write this as I can factor m dot and write it as m dot u out minus u in plus, so get rid of the sigma, and for one dimensional, if you have like one dimensional flow, something like this, right? It's just one place, right? So it's like here it comes in and here it goes out, right? So I can simplify it as follows: m dot, I can just factor m dot, then it's going to be u out minus u in plus p over rho out minus p over rho in plus v square out minus v square in over 2 plus gz out minus z in, right? This equals to this. This is for inflow and outflow. By out and in, I mean that. And so this is the equation we have. And now I can make some further assumptions and obtain very interesting forms. So here, if you see from now, if you look at it carefully, this really looks like what equation? It looks like Bernoulli equation, right? So let me write this down. Mechanical energy and Bernoulli. Okay, so for a steady flow, so for Bernoulli, we could only write it for a steady flow, right? There is also some versions which we have unsteadiness that is kind of combined with that, but we are not gonna study that in this course. So for a steady, incompressible, which means that incompressible means that the density is not changing, so we have to say rho out. Again, this is a simpler definition of that. So the real one is d rho over dt is 0, but here I will just assume that is constant. So rho out equals to rho in equals to rho, or another one is the divergence of u is 0, which is kind of a more general definition of that. But for now, let's just assume incompressibility means that the density is constant. So for an incompressible flow and a steady, we have the time change of anything is going to be 0, right? So this is for a steady flow. So if you have this condition, then this term is going to be 0, right? So I can just write down the energy equation as follows. So energy equation reduces to what? So the first term is going to be 0. So I have only this term plus these terms, right? And this term, I have already written it as like this. And then for a one-dimensional flow, I made it like this, right? So I just want to integrate all of them together. So this is going to be my only left-hand side. So I have m dot u out minus u in plus p out over rho. Rho is constant here because we have an incompressible flow. P in over rho plus v square out minus v square in over 2 plus gz out minus z in equals to the right hand side, which is what? Which is q dot net plus w dot shaft, right? So q dot net in plus W dot shaft net in, right? Okay. So now if we define this small q dot net in as the total nets q dot net in, which is heat transfer over m dot, the mass flow rate, I can write this equation as follows. It's going to be P out, outflow, over rho plus V square outflow over 2 plus GZ out equals to P in over rho plus V square in over 2 plus GZ in minus U out minus U in minus Q dot, let me write this as just Q net net in and then this one is gonna be plus let me see, yeah, plus W dot shaft in, okay. And what is this? This is what we can say, this is loss of useful or available energy due to friction, right? So this is the internal energy. How much is it lost, right? And then the total heat, which is how much is it kind of lost and has been converted to heat, right? So this is what we call is loss of energy or useful or available energy because of friction. And this is just the work done on the system, right? Like if you have a shaft or something that is kind of gonna elevate the energy in the system, okay? So if we assume no external work on the system, that means the W dot shaft is 0. Say we don't have any shaft, and we will investigate that too, like for pumps. Then we can write this as is 0. Then we can write this as P out over rho. Let me see if I can copy this. That would be easier. Yeah. Minus, instead of that formula for internal energy and heat, I just write it as loss. Loss of available energy, okay? And what is this? If you look at it, this is very important formula. This exactly Bernoulli equation, but with this additional term here, which is loss term. So this is a more general form of Bernoulli that we previously derived from Newton's second law of motion, second law of motion for a steady incompressible fluids, but now with friction. So previously we had assumed it was inviscid, right? But this is a more general form of Bernoulli that also accounts for frictional force, which is this last term in the system that you also account for that, okay? So Bernoulli is only valid is only valid for inviscid, which means no viscosity fluids. But this formula that we derived is a more general form of Bernoulli that also accounts for these kind of losses in the system or friction in the system, okay? So now I want to investigate this external work as well, or this shaft. So this is what we also call it as pump pressure, okay? So we had the work done by the pressure itself, and also we have the work done by the pump pressure. So let's see what it is. So pump pressure, let's see how we can add it. And this is something very important that we are going to use in the formulas to drive water pumps, okay? So pumps can add energy to fluids, okay? So power of pump is defined as what is work over time, right? Power is work over time. And we can show that, so work over time, what is work over time? This is the time rate of work, right? So we can just show it with W dot or W dot of pump, right? The power of pump equals to W dot of pump, which is work per time of that, okay? And you know from, again, thermodynamics that power equals to force times velocity, or F times F dot V, right? And F equals to what? F is pressure, force is force, right? So it's going to be pressure times A dot V, right? So this is pressure. So instead of F, I can write PA, which is going to be pressure times area. Again, the definition of pressure is force per area, right? So I can write this like that. This is pressure, this is not power, don't confuse that. And now, and interestingly, this is gonna be Q, or discharge, right? We had it as well before. So the power of the pump, which we may show that, or some problems just give you the power, is what? Is just W dot, sorry, this is not power, this is the pressure, pump pressure, okay, is gonna be W dot over Q. So this is pump pressure. Or simply also we can write a pump head as HP equals to W dot of pump. So this is W dot of pump or shaft, which we called it before, over what? So instead of pressure, you can write rho GH, right? Pressure is rho GH. So if I want to find HP, is going to be rho GQ. So this is going to be pressure. Sorry, this is going to be pump head. Okay, so in some problems, they might ask you, what is the required pump head, for example, to do this, or like take water from one place to another place. So what do we mean by pump head? Is just this. So they might give you the power of the pump, which is W dot, right? And then they want you to calculate the pump head, which is going to be this, or they might ask you to calculate the pump pressure, which is going to be this, right? So these are two important formulas for pump pressure and pump head, which you need to remember. Okay, so let me put it here. Okay. So this is how this W dot of the shaft also comes. So this will be added to the right-hand side of the Bernoulli equation. And I'm going to show one example of that at the end of this session. But before that, I want to also define some of these energy losses that we might experience in some of the vents or some kind of engineering problems. Okay, so let me just introduce these loss coefficients for vents. So say if you have a vent like this, okay, and let's see. Okay, and so we have, say, section 1 here and section 2 here, and we have the fluid that is moving like this, and so it goes out from here with a velocity v2. So if you take this, say, control volume again, what we can write is energy equation between 1 and 2. So let me put this a little bit down. So energy equation. What is going to give me? This is my energy equation, so let me copy it. Or let me just write it down here again so you remember. It's just Bernoulli P2 over rho plus V2 square over rho over 2 plus GZ2 equals to P1 over rho plus V1 square over 2 plus GZ1 minus loss between 1 and 2. What is the loss? Okay, energy loss here. So we can assume that V1, again, because A1 is V1 A1 equals to V2 A2, and A1 is much greater than A2, so we can assume that V1 is much smaller than V2, or V1 is almost equal to 0. Okay, so we can just neglect that. And the other thing I can make is that Z1 and Z2 are almost in the same elevation, so I can just assume they are going to cancel out. And so from this formula, again, P1 and P2 are, say, almost like equal, or like in the atmospheric pressure. So I can say, I can estimate the loss of this vent as follows, as a function of V square, V2 square, which I call as KL times V2 square over 2. Right, so you can assume P1 is also about 0, or they are small, or it doesn't matter, even they are there. So we can just define a loss coefficient here. And so this is going to be KL times V2 square over 2. And we call this as loss coefficient. Okay. And so KL, this loss coefficient, is 0.5 for cylindrical, something like this. If you have, you are going to lose a lot of energy, like half of your energy, if you have something like this vent. So the fluid is comes from here. And then goes out. And so you are going to lose half of your initial kinetic energy in this vent, like cylindrical vents. And KL is going to be about 0.05 for rounded cylindrical vents. So rounded cylindrical. So something like this. If you have these kind of vents, then your loss of energy is much smaller. So it's only 5% of your initial velocity or kinetic energy is going to be lost if you have this kind of vents. Okay, so this was one example that we can use energy equation here. And so this is called again energy equation because we have loss, so it's not Bernoulli. Bernoulli is only for inviscid fluids. Okay, so now let me solve one example of this so you better understand how you should use this energy equation, and especially in the context of pumps, because we will use this for the kind of designing pumps. Okay, so this is a very important formula for pumps that we learn, and also energy equation. Okay, so let's me get started as an example. So the example that we have is as follows. Determine the flow rate and B, the power loss associated with the following flow. Okay. So what do we have here? We have two reservoirs, one reservoir 1 and second reservoir 2, and we have water here. And what happens is that reservoir 1, we are pumping the water from reservoir 1 to reservoir 2, which is at a higher elevation. Okay, so what we want to determine is the flow rate and also the power loss associated with this flow. Okay, so power adds 10 horsepower, and the elevation difference between two reservoirs is 30 foot. So this one is 30 foot at a higher elevation compared to this one. Okay, and the head loss we know by the, for example, by the frictional forces that act in the system is 15 foot. So 15 foot of the energy is wasted through these pipes, friction in the pipes, and also pump and air and all the system. Okay, so this is our energy loss, and then we have this elevation difference that we have to overcome, and the power adds 10 horsepower to kind of carry this water up. Okay, so now let's start and see how we can find the flow rate, and we want to find the first flow rate in this pipe, and also the power loss associated with this friction. So power loss with the following, with the friction in the following flow. So let me write it down. With the friction in the following flow. Okay, so let me get started. So A is we want to find the flow rate, or Q. So we start with energy equation. So energy equation states P2 over rho G plus, I divide everything by G. okay, plus v squared 2 over 2g plus z2 equals to p1 over rho g plus v1 squared over 2g plus z1 plus what? Plus the head of the pump. Why I divided everything by rho g? Because I wanted to convert everything to head. So this was one form of Bernoulli equation, if you remember, because now everything is in terms of z, or elevation, or head, or meters, or foot, depending on your dimension, right? And the reason I did that, because here the problem gives me the pump head, right? This has given me the pump power, right? So 10 horsepower, but also it gives me the elevation, and also it gives me the head loss, right? So I know how much of the energy is lost, but it gives me the head of that. So it's like in terms of 15 foot, right? So I can just add that, I can just reduce that energy. So it's going to be minus head loss, which is how much it is lost. And then I know that the pump also adds power or horsepower to this kind of system here for P1, right? So whatever I have here, the system adds power, and then it goes to the second location at 2, right? Reservoir 2. So I add that as HS, which is what? Which is pump head, right? We had it before. It's pump head, which we define it here. Or maybe let me just write it as HP, so you better understand it with previous one, okay? So because we have two big reservoir, I can assume that V1 is small at reservoir 1. So say we are starting from here, and then we go here, right? So it's not, because it's too big, it's too large. Let me maybe write it from this place, okay? So I want to write it from this place to this place, okay? So we have this flow that is going here. So because these two reservoirs are too large, we can assume that V1 is equal to V2 is almost equal to 0, because large reservoir. And P1 equals to P2 equals to atmospheric pressure, right? And it's 0 in terms of gauge pressure, right? Okay, so if I have these assumptions, the whole energy equation reduces to H pump equals to HL, which is loss, plus Z2 minus Z1. Okay, and pump head, we know, is defined as, we had a formula here, so let me just copy that. It's W dot pump over rho GQ. So it's going to be W dot pump over rho GQ. Instead of rho G, I can just write the specific gravity of water. So it's going to be gamma W dot times Q. Okay. And so now I have everything. I can get the W dot of pump, or it is what we call also shaft in. So let me write it down again. Shaft in equals to shaft net in equals to, so we have that its pump adds 10 horsepower, so it's going to be 10 horsepower. Okay, so in order for you not to this horsepower is actually a unit, so in order for you not to confuse that, I'm just gonna write this as HS. Okay, because you might confuse that with this. I don't know why it's not working. So let me just continue and then I will do it later. 500. Then I have, I want to do, so you have to convert that horsepower into foot and pound. So it's going to be one horsepower is 550 foot-pound. So this is the conversion rate of that, over gamma W of water is 62.4 pound over foot cube times Q. Okay, so this is going to give me 88.1 if you calculate it over Q. Yeah, it's weird. Okay, so I just write this as S. So now I have everything I need. So instead of H, this is also HS. So instead of HS, I write 88.1 over Q equals to HL, which is how much head loss, which we have as 15 foot. So I just write it down. 15 foot plus the elevation difference, which is 30 foot. So from here, I can find Q, or the flow rate in this system, in the pump, which is going to be 1.96 foot cube per second. And then the second thing was find the power loss associated with the friction in the following system. How much of the power of the pump is lost just because of the friction and not the elevation difference? Let's calculate that. So W dot of loss is what? Is gamma W Q H of loss, right? This is how much of the water, how much of the loss, head loss, the work associated with the head loss of the system, right? You have this formula here for pump, and this is going to be for the head loss, okay? This is for the pump head, and this is for the head loss. Similar to that. So we can just calculate that. It's going to be 62.4 pound per foot cube times Q, which we found it from here, is going to be 1.96 foot cube per second, times how much is it? How much is the head loss? Is 15. So I just write it down. It's 15 foot. It's going to be 1830 foot pound per second. And then if we want to convert this to horsepower, we can just use the conversion formula. 1 horsepower is 550 foot-pound per second. So we have a second here too. So this is gonna give us 3.33 horsepower. So 3.33 horsepower of the 10 horsepower was just wasted due to friction in this system. Another way to calculate it is, this just came to my mind here, is you have this much head that is kind of pumped by the pump, right? This is charge or provided by the pump. This is the head, the total head, right? So the pump is actually elevating the system with 45 foot. And 30 foot of that is associated with the elevation difference, and 15 foot of that is associated with the head loss. So another way to calculate it is going to be 15 over 30 plus 15 foot is associated with the head loss, right? So what is this? It's going to be 1/3 of the total horsepower is associated with that. And what is the total horsepower? Is 10, right? 10 horsepower. So this is going to give me exactly this, 3.33 horsepower. Okay, so this was another trick that you could use to solve this problem, but I just wrote down the more general form of that, so you are able to solve other problems as well with these formulas. Okay, so this was the energy equation. So let me just briefly review what we learned today. So we started with the energy equation with the first law of thermodynamics, which states time rate of increase of the total stored energy of the system equals to the net time rate of energy addition by heat transfer into the system plus net time rate of energy addition by work into the system. Okay, so and then we just wrote down this in terms of mathematical symbols, which is the total energy, the time rate of change of the total energy of the system equals to the net heat transfer and net work on this done on the system. We can write the total energy of the system as sum of the internal energy plus kinetic energy plus potential energy per mass, and then integrate that. And also we can decompose the total work done in the system by work done by the pressure, which I show it as minus integral over the control surface of PV dot NdA plus the work done by the tangential stresses or shaft or pump in the system. And then we can use the Reynolds transfer theorem for this equation, and this is going to give me this general form of the energy equation. And then for a one-dimensional flow, we can write this as m dot and then times this equation. And then for a steady flow and incompressible, for a steady flow, we can just neglect the first term in this equation because it's steady, it's not changing with time. And then for a one-dimensional flow, and also incompressible flow, which means that the rho is not changing, we can write that energy equation reduces to this form. And then we can rearrange the terms, and finally we get to this equation, which shows that without external work, but we can also add that, This is just a modified, a general form of Bernoulli equation, which we call it actually energy equation, which also has the last term due to frictional forces. And then we define the pump, which is the power which is added to the system, like through shafts. And so we define that as the pump pressure is W dot the work, the time rate of work, or the power of the pump, over Q, which is the discharge. Or we can show the pump head is W dot of pump over rho GQ or gamma Q. And then this was just a simple thing for the loss, calculating the loss in vents, and we showed that the loss coefficient for a rounded cylinder is smaller than the cylindrical. And then we solve an example of pumps where we have also head loss, friction, and also elevation difference in the probe. Okay, so this was the end of this chapter, chapter 5. So we have done the Bernoulli equation. We now know the Bernoulli equation and also the modified form of that, which is, we found this from the energy equation, as well as the linear momentum equation and also continuity equation, okay? So after this, I will briefly review chapter 6, which is conservation of mass in differential form and also conservation of linear momentum in differential form, but I'm not going to go through too much detail into that because that's kind of out of the scope of the course, but I will just mainly review the conservation of mass in differential form and not the kind of the momentum conservation of mass in differential form, which we call it Navier-Stokes equation. And so far we have what we have learned for conservation of mass and momentum were in integral form, and in the next chapter and next topic we will work on and see these conservation laws in differential form.